One of the most popular buildings in the Middle East and the world, a silver needle piercing the dusty Arabian sky. It is more than a building, it is an engraved symbol of oil triumph and boundless ego. We are sold an ideal picture of engineering victory, frozen in glass and steel. But height lies, hiding the true price of verticality. From the ground, it is impossible to see how the tower groans under the strain at the 160th floor. It is constantly moving, deflecting by 1.5 meters to avoid breaking. At this height, the wind behaves not like air, but like a dense, viscous liquid.
Behind the glossy facade lies not luxury, but the intense work of a giant survival machine.
This is not a house, it is a complex exoskeleton for people. This tower stands on sand, which according to the laws of physics, should not be able to support such a colossal weight. It has to contend with a vortex path capable of rocking and destroying the concrete skeleton in resonance.
Its cooling system produces so much condensate that it could fill Olympic swimming pools.
The elevators here are designed so as not to rupture passengers' eardrums with the speed of ascent. Burj Khalifa is not just a hotel, office center, or observation deck. It is a vertical city-state with its own weather and its own laws of physics. It is a closed ecosystem that constantly sweats, vibrates, and resists the environment. Let's go back to square one. When there was nothing on the horizon, there was no glass, no concrete, no ambition to rewrite the Guinness Book of Records. There was only a sun-scorched desert, an old military base, and the Sheikh's idea to turn oil dollars into stone. The geology of Dubai is a real nightmare for any skyscraper builder. There is no bedrock here, no granite slab like in Manhattan.
Underfoot, there is only loose sea sand and weak, porous sandstone. Building the world's tallest building here is madness from a structural engineering point of view.
Engineers faced an unsolvable paradox. A traditional foundation simply would not work here. There was nothing to support a building weighing 500,000 tons. It would begin to sink into the ground immediately after the first 10 floors were built. The solution had to be found not in the strength of the support, but in the force of friction.
The principle they used is called suspended piles, and it is frightening in its boldness.
192 concrete columns were driven 50 meters into the ground. They do not rest on solid ground at the bottom because there is no solid ground there. The building is held up solely by the lateral friction between the surface of the piles and the compressed sand. This was the first and most risky venture of the project. The friction calculations had to be perfect. An error in the coefficient of friction of even 1% would have meant a slow disaster. The tower could have started to sink or tilt years after completion. But soft sand is not the only deadly threat to the foundation. The groundwater in Dubai is extremely salty and chemically aggressive. The concentration of chlorides and sulfates there is higher than in seawater. This mixture can eat away at ordinary concrete and turn steel reinforcement into rusty dust in a couple of years. The foundation had to be a chemically inert bunker capable of lying in acid. A special concrete mixture with microsilica added was developed. It makes the structure so dense that water molecules cannot physically penetrate the pores of the stone. It was not a construction project, but high-achieving chemistry. But even super dense concrete did not seem sufficient to the engineers to guarantee protection. They implemented an active cathodic protection system. A weak direct current is passed through the foundation reinforcement around the clock.
This current suppresses the electrochemical reaction of metal oxidation. The building literally stands on an electric chair to prevent it from rotting from below.
If the current is turned off, corrosion will begin immediately. The foundation is a living battery that requires a constant power supply. Once the foundation issue was resolved, the main problem was not gravity, but aerodynamics. At a height of 800 meters, wind is not just a stream of air. It is a powerful physical force with tremendous kinetic energy. The main enemy of any super tall skyscraper is the phenomenon of resonance. Wind flowing around a rectangular building creates low-pressure zones behind it. These are Kármán vortices, which break away from the corners one after another. These vortices begin to rock the tower left and right at a certain frequency. If the frequency of the wind blows coincides with the natural frequency of the building's vibrations, the structure will collapse. The glass will shatter, the concrete will crack, and the frame will lose its rigidity. Adrian Smith, the project's chief architect, realized that fighting the wind with brute force was useless. The walls cannot be made infinitely thick. The wind should not be stopped, but tricked. The traditional prism or rectangle shape was immediately rejected as suicidal. The building needed a shape that would confuse the wind, preventing it from gathering into a single stream. The solution was a Y-shaped structure at the base. It was inspired by the local desert flower, the Hymenocalyx. But this is not bionics for beauty's sake. It is pure, rigid utilitarianism dictated by the wind tunnel. 3 wings radiating from the central core create an incredibly stable tripod. Engineers called this system a buttressed core. Each wing supports the other 2, preventing them from twisting. But one base shape was not enough for a height of 828 meters. The architects used another trick. The floors of the tower taper unevenly. The terraces recede in a spiral at different heights on each side. This breaks up the wind flow, splitting it into many small, chaotic streams. The wind can never organize itself into a single powerful vortex that hits the entire height. At each level, it is confused, forcing it to flow around the building in different ways. The tower literally throws off the wind like a judo wrestler throws off an opponent's grip. Without this complex geometry, a building of this height would be physically impossible to construct out of concrete. It would either collapse or cause seasickness in all the inhabitants of the upper floors. Construction began at a frantic, almost military pace. The schedule was tighter than any other construction project in history. A new floor every 3 days. This required logistics that pushed the limits of human capability and metal endurance. The construction site turned into a vertical conveyor belt that never stopped. Thousands of workers moved like ants in a strictly defined rhythm. Reinforcement workers knitted the frame, followed by formwork workers, followed by concrete pumps. To keep up with this pace, self-climbing formwork technology was used. Hydraulic jacks lifted the forms and platforms upward as soon as the concrete set. The tower grew like a living organism, pulling itself out of the ground. But with every meter of elevation, the price of any mistake grew. Logistics at a height of 500 meters becomes a nightmare. It took hours to lift a bucket of bolts to the top. The cranes also had to grow along with the building. They were installed in elevator shafts and lifted themselves hydraulically. Crane operators lived in cabins at height for days on end. Going down for lunch or to the toilet was too time-consuming and expensive.
The main problem was the verticality of the elevator shafts. At such a height, even a deviation of a couple of centimeters at the bottom
would lead to a meter-long skew at the top. An elevator in such a shaft would simply get stuck or crash into the walls. Conventional surveying instruments and lasers did not work here due to the tower's vibrations from the wind and cranes. GPS satellites provided too much error for millimeter accuracy. Engineers had to invent a new coordinate system. They used a real-time monitoring system that even took into account the movement of the sun. During the day, the south side of the building heated up and expanded, and the top of the tower tilted northward. The building bowed to the heat, moving away from the sun. The concrete pour had to be adjusted to account for this thermal dance. The main enemy of the material was the extreme Arabian heat. The temperature in Dubai regularly rises to 50 degrees in the shade during the day. Concrete is not just clay, it hardens as a result of an exothermic chemical reaction. As it hardens, concrete releases heat. If you add external heat to this, the mixture boils. It begins to set in the pipes before reaching the formwork. This is called flash set, instant setting. If this had happened, hundreds of meters of high-pressure pipes would have turned into a monolith. They would have had to be cut out and replaced, halting construction for weeks. Pouring concrete during the day was strictly prohibited by the engineers. The work was completely moved to nighttime, when the temperature dropped to at least 30 degrees. But even that was not enough for a quality reaction. The engineers took an unprecedented step in the history of construction. Instead of water, crushed ice was added to the concrete mixture at the plant. Huge chunks of ice were crushed on an industrial scale and mixed in mixers. The goal was to cool the solution before it entered the pump. The ice melted during the mixing process. evenly moistening the mixture and lowering the temperature to a critical 15 degrees. It was a viscous, cold gray smoothie that had to be thrown into the sky. But lifting this ice concrete to a height of 600 meters was no trivial task. The most powerful concrete pumps in the world had to be created. The pressure in the pipes reached a monstrous 200 atmospheres. For comparison, this is the pressure of water at a depth of 2 kilometers. The walls of the steel pipes wore down at an incredible rate from the friction of the rubble. If the pipe burst under such pressure, the jet of concrete would act like a projectile. It could cut a person in half or knock down a load-bearing wall. The pump operators worked blindly, relying only on pressure sensors and radio commands from above. They had to feel the rhythm of the building. The slightest blockage in the pipe required an immediate response. Otherwise, the system would rupture. By 2007, the gray concrete skeleton had reached its design height. But a skeleton cannot live in the desert without protective skin. The Burj Khalifa's facade consists of 26,000 unique glass panels. Each panel is cut by hand and has its own unique code. The glaziers faced a contradictory task. They needed to let in as much light as possible, but reflect the deadly heat of the desert. A special composite glass with silver coating was created. The thinnest layer of silver acts as a mirror for infrared radiation, blocking heat. A layer of titanium was added to the outside to withstand sand and wind. But installing the panels turned into a daily feat of mountaineering. At altitude, the wind was unpredictable and fierce. The half-ton panels swung on crane cables like pendulums. Workers had to catch them by hand, hanging over the abyss with no room for error. One wrong move and the panel would smash into the facade, showering the city with a rain of shards. Installation continued around the clock to close the building's outline. When they began to enclose the building with glass, a hidden aerodynamic problem arose. The ceiling created a powerful stack effect. The difference in pressure and temperature at the bottom and top created drafts, like in a furnace. The air whistled as it tried to rush upward through the elevator shafts and stairwells. If you opened the door to the lobby, the gust of wind could knock a person off their feet. This draft could block the elevator doors by pressing against them. In the event of a fire, this effect would instantly spread smoke throughout all floors in minutes. Engineers had to create a complex system of airlocks and vestibules. They began to inject artificial air pressure into the floors to balance the physics. In 2008, when the tower was nearing completion, the global economy collapsed. The financial crisis hit Dubai with the force of a tsunami, destroying the real estate market. Credit lines were frozen and investors fled in panic. Construction, which was burning through millions of dollars a week, was on the verge of a complete halt. The symbol of wealth risked becoming the world's tallest unfinished building. Burj Dubai stood dark, like a rebuke to the Emirates' ambitions. The city was effectively bankrupt, unable to pay its contractors. Salvation came from its wealthy neighbor, the Emirate of Abu Dhabi. Sheikh Khalifa allocated billions of dollars to save Dubai's economy from collapse. But help in the world of big politics is never free. The price of salvation was symbolic but painful for Dubai's pride. On the day of the opening, the signs with the name Burj Dubai were urgently dismantled. The building was officially renamed Burj Khalifa. It was a permanent reminder in concrete. Even the tallest building in the world cannot stand without a foundation of money. The pride of Dubai now bore the name of its creditor. The final stage of the race was the installation of the spire. This is not just a decorative antenna, it is the completion of the architectural appearance and part of the grounding system. The spire weighs 4,000 tons and is made of thick steel. It was physically impossible to lift such a mass to a height of 700 meters with conventional cranes. The wind there is so strong that the crane boom would simply fold in half. The engineers had to use a previously unseen telescope method. The spire was assembled inside the building itself, in a hidden shaft, section by section. Then powerful hydraulics pushed it up from below. It emerged from the top of the tower like a rod from a mechanical pencil. It was a triumph of precision engineering, but real people were working at the top. They welded joints on narrow beams, at an altitude where commercial airliners fly. The wind knocked them off their feet, and the cold penetrated to their bones. Official statistics are shamefully silent about the number of injuries and deaths among workers. Migrants from India, Pakistan, and Bangladesh built this symbol of luxury for pennies. Their labor is the invisible mortar that binds these blocks together. They worked 12-hour shifts, living in crowded camps in the desert. They will never be allowed to enter this building through the front door. Deep economic inequality is embedded in the DNA of this building as firmly as steel reinforcement. Today, with construction complete, the building functions as a giant pump. Delivering water to the 161st floor is an engineering challenge. It cannot be pumped from below with a single powerful pump. The pipes would burst from the pressure of 100 atmospheres. The water is lifted in cascades, transferring it from level to level. Huge tanks on the technical floors serve as transfer points. Gravity is the main enemy of the water supply system here, and it is fought every minute. But an even bigger problem for engineers is condensation. In the hot and humid air of Dubai, the cold surface of the building sweats like a soda can. Every day, tons of water form on the facade. The system is designed to collect every drop of this condensation. Pipes drain the moisture into an underground reservoir. This amounts to 50 million liters of distilled water annually, which is used to irrigate the park. The building literally drinks from the air to maintain its gardens. The elevators are a separate engineering drama and compromise with physiology. They are the fastest in the world, 10 meters per second, but their speed is limited by human biology. If people are lifted faster, the sudden pressure change will cause unbearable pain in their ears. The elevator cabins are airtight and have an aerodynamic capsule shape. This is necessary to reduce air resistance in the narrow shaft during movement. They work like pistons in an engine cylinder. The building's sewage system has also been the subject of urban legends and engineering debates. For a long time, there was a myth that the tower was not connected to the city network. It was said that sewage was removed daily by columns of orange trucks. The reality was more complicated, but no less dramatic. The city's sewer system really couldn't handle the sudden discharge from the vertical city. The area's infrastructure was bursting at the seams from the load. In the early years, the load on the sewage system was critical. The building had to wait until the city upgraded its old guts to meet its needs. This is a classic example of how the ambitions of a single facility outpace the capabilities of the surrounding system. Today, Burj Khalifa is an established fact of reality. Tourists climb to the observation deck, drink coffee, and take selfies against the backdrop of the clouds. For them, the building is static and immovable, like a mountain. But the engineers monitoring the sensors know the alarming truth. The building constantly breathes and moves. The amplitude of the top's oscillation in strong winds reaches 1.5 meters in each direction. This is not an accident, but a cold calculation by the designers. If the tower were rigid, it would break during the first storm. It must be flexible like a reed to dissipate the energy of the wind. Maintaining the facade is a never-ending Sisyphean task. Special machines hidden in technical niches release cradles with washers. It takes the team 3 months of continuous work to wash the entire building once. As soon as they finish at the bottom, the glass at the top is already covered with dust again. Sandstorms act like sandpaper, polishing the glass and making it matte. Ultraviolet rays mercilessly destroy silicone sealants. The building ages faster than normal houses due to the extreme operating conditions. The tower's energy consumption during peak hours is equal to that of a small city. In the era of the green agenda, Burj Khalifa looks like an environmental crime. It is a giant glass thermos in the scorching desert. It needs to be forcibly cooled 24 hours a day, 7 days a week. If the air conditioning system fails, the building will turn into a solar oven. Burj Khalifa is a monumental monument to a bygone era, an era when size was of absolute importance and resources seemed endless. It is the pinnacle of ego architecture, the desire to prove superiority through height. Modern skyscrapers strive to be smart, green, and sustainable. Burj simply strives to be taller than everyone else, at any cost. It is the philosophy of the last century, cast in the concrete of the 21st. We look up at it and see the greatness of the human spirit. But if you put your ear to the walls of the technical floors, you can hear the truth. The hum of powerful pumps, the whistle of the wind in the elevator shafts, and the creaking of metal. At night, when the temperature drops, the steel spire cools and contracts, making noises. This building is not a triumph over nature, as we would like to think. It is a fragile truce, bought at a huge price. This is armed neutrality, supported by billions of dollars and millions of kilowatts of energy. The sand that holds the piles in place by friction is still unstable. The wind is still searching for a weak spot in the geometry. The salt in the groundwater is still eating away at the protective layer of concrete. The tower stands as long as the machines inside it and the people around it are working. As soon as the pumps stop, the desert will begin its attack. As soon as the cathodic protection is turned off, rust will begin to devour the foundation. The desert knows how to wait. It is in no hurry. It will begin its slow but inevitable return, taking back what is hers. But for now, looking at the spire reaching into the stratosphere, we are willing to forgive this structure for its price, because it is human nature to build towers of Babel, even knowing how that first story ended.